Welcome to Regents Review Unit 7, and our focus is on heat. Recall that heat energy goes from hot to cold, and that average kinetic energy is a measurement of temperature. So looking at our example here, our room temperature is 22 Celsius. We have hot chocolate at 80 Celsius and ice cream at -4 Celsius. So since heat flows from hot to cold, in the hot chocolate situation, the heat is going to be lost or transferred to the environment. And for the ice cream, since the room temperature is warmer, it's going to transfer heat to the ice cream, warming it up. In terms of heat and our reactions, we have two terms. We have endothermic and exothermic. And we also have table I, which has the heat of our reactions, the delta H, which tells us if something is endothermic or exothermic. So endothermic is taking in or absorbing heat, and we'll find heat or energy on the left-hand side of a reaction, on the reactant side. If it's not listed as such here, then you can look it up on table I, as we can see here, and we look for the delta H value. Now at the bottom of table I, it reminds you that a minus sign indicates an exothermic reaction. So a positive sign then would be an endothermic reaction. So this is taking in energy in order for carbon to bond with hydrogen to make C2H4. Exothermic is a release in heat. Heat is on the right-hand side of our reaction, as we can see here. So it's producing heat. It's giving it off. You'd feel this substance being hot. Exo like exit, so it's exiting heat. Again, if it's not listed in the reaction, you can go in table I, and you can see here that the delta H is -393.5, so we know it's exothermic, and then I know to place my heat energy on the right-hand side. Looking at our phases of matter, when we talk about solids, as you can see here, solids have a definite shape and volume. They have the strongest forces of attraction between the particles, and that's what keeps them together. They are moving, just kind of vibrating in place. There's not a lot of potential for movement for solids. Liquids are more spread out, so more entropy. They have a definite volume, but they always take the shape of their container. And they have a moderate force of attraction between the particles. They have more ability to move due to the spaces between them. Gases, lastly, have no definite shape or volume. They always fill the container. There's a lot of space between them. They have the most potential for movement, and they have the weakest forces of attraction between the particles holding them together, and that's why they're so spread out. Looking at our phase changes, let's focus on endothermic first. So we're going to add heat as we go left to right. So when I have a solid and I start adding heat to it, eventually it's going to get to the phase change, and it's going to turn into a liquid, and we call that phase change melting. Liquid, if I keep heating that liquid now, and I get to the phase change to turn to a gas, we call that boiling or evaporation. And there's also a process where we can go right from a solid to a gas for certain substances, like solid carbon dioxide, known as dry ice, or our solid iodine, where it skips the liquid phase and goes right from a solid to a gas, and that's our sublimation. And now if we cool our gas, so let's talk about that unique situation. If we cool our carbon dioxide, it's going to go right from a gas straight to a solid, and we call that deposition. For most other substances, when we cool a gas, it's going to then condense, so condensation, to a liquid, and then keep cooling it, keep removing heat, exiting heat. It's going to go from a liquid to a solid, and we call that freezing. In talking about the specific heat of a substance, we focus a lot on the specific heat of water, and in comparison to metals. The specific heat is the amount of heat needed to raise the temperature of a gram of a substance 1 degree Celsius. And for water, we have the specific heat listed on table B, which is on the front of our reference table. The higher the specific heat means the more energy it takes and the longer it takes to heat and cool down a substance. So water has a very high specific heat capacity in comparison to other things like metals. Metals heat up very quickly and cool down very quickly, hence they have a low specific heat. The heat of fusion was the amount of heat required to go through that phase change, that solid to liquid phase change, aka melting. And the heat of vaporization is the amount of energy required to vaporize something, to turn it from a liquid to a gas. And those values are also listed on table B. And these are all for water. So now looking at our heating and cooling curves, here's our heating curve. As we add heat over time, we see temperature increases, and then our cooling curve here. We could see that temperature, our average kinetic energy, is going to increase, and then when we get to our first phase change of melting, we see that we get a plateau. So this is going to be where our heat of fusion is, how much heat to get through this phase change. Once we get through the phase change, we're a liquid. We can keep increasing temperature, and then we get to our heat of vaporization. Once we get through that phase change, then we turn to a gas, and we can further increase our temperature. So since temperature is a measure of average kinetic energy, then all of the places, the solid, the liquid, the gas, all these places here where temperature is increasing, kinetic energy is increasing. Potential energy then, through segments A, B, C, D, and E, F, is just staying the same. When we get to our phase change, we notice that temperature is not increasing, so kinetic energy is not increasing. So what is increasing during our phase change? Our potential energy. So potential energy increases during the phase changes. So potential energy, phase change, plateau. And then just the exact opposite here. So then as we start from a gas and we take away heat, we cool it, we first condense, and then we freeze. And make sure you can label these solid, liquid, and gas as well. So how do we calculate the amount of heat required to change the temperature of something or to get it through a phase change? Well, we have three formulas listed on table T. We have Q equals mc delta T, and we have Q equals mHF, and Q equals mHV. Notice on the heating curve that the mc delta T questions are where the temperature is changing, in this case increasing. So how do you know which formula to use? When there is a change in temperature, we have to use the change in temperature calculation, which is Q equals mc delta T. Delta T, again, meaning change in temperature. If there's no change in temperature, like here and here, we have to use either mHF or mHV. So some key words to look for when it says at 0 degrees Celsius. So how much heat energy is required at 0 degrees Celsius, or freezing or melting. If those words are used and there's no change in temperature, we're using the heat of fusion, so it's Q equals mHF, where m is the mass and HF is the heat of fusion from table B. If it says at 100 degrees Celsius, or boiling, or vaporizing, or even condensing, that's all occurring at this phase change, and we're using the Q equals mHV. Again, m is mass, HV is the heat of vaporization on table B. So let's see an example. How much heat is needed to raise the temperature, so we're changing the temperature, of 500 grams of water from 5 Celsius to 20 Celsius. So once I know that's a change in temperature, I know I'm using Q equals mc delta T. I can list out my variables. So m, my mass, was 500 grams. The specific heat, C, of water from table B is 4.18, and our change in temperature from 5 to 20 is 15 Celsius. Then I'm just going to plug in these values into my equation, Q equals mc delta T, and I get 31,500 joules, or if you're rounding to proper sig fig, 32,000 joules. So this change in temperature from 5 to 20 Celsius is occurring right over here. Right, so we can see that there's a change in temperature. That's why we're using this Q equals mc delta T. This question here, how many joules does it take to melt a 16-gram sample of water at 0 degrees Celsius? So we have two keywords here, melt, 0 degrees Celsius, there's no change in temperature. That's my heat of fusion, so that's Q equals mHF. So then I plug in my mass, which is 16 grams for m, and then my heat of fusion from table B is 334 joules per gram, and I get my heat of 5,344 joules. How many joules does it take to boil a 250-gram sample of water at 100 degrees Celsius? So now we have keyword here, boil and 100 degrees Celsius. We're looking at this phase change here. How much heat energy does it take to get through this, to go from a liquid to a gas? So our mass is 250, we plug that in. Heat of vaporization from table B is 2,260, and we get an answer of 565,000 joules is required to take 250 grams of water to go from a liquid to a gas.